Welcome to EDU World Space.
So the expression for electric potential at any point due to the charged hollow sphere can be represented by this following expression. So the potential is equal to Coulomb's constant times charge over the radius of the sphere. So now to answer part A, let's go to part A. So if the voltmeter is connected between the points A and B, then the potential difference between A and B can be defined by this following expression. And so now it'll just be KQ over R minus KQ again over R, and this is just equal to 0. So the potential between the points A and B should be 0, and the voltmeter should be reading 0. So now if you move on to part 2 of part A, so if the voltmeter is connected between the points BC, then the potential difference between BC is also similar. So once again, it'll just be the same thing and it'll equal 0. So the voltmeter should equal 0 at any point on the surface. So now if you move on to part 3, the potential at infinity should be 0, because if you take a look at this, so the potential at infinity is equal to VC minus the potential at infinity. So if you substitute the value of KQ over R, and we know that the potential at infinity is 0, so it's just minus 0. So now let me know. So the potential. So we now know that the potential between C and infinity, between the point C and infinity, is just equal to KQ over R, and we know the constants of these. So let's just go ahead and plug it in. So the Coulomb's constant, 9 times 10 to the power 9, times the charge, which is 150. So this is microcoulomb, so it's times 10 to the power negative 6. And this is over the radius, which is 60 centimeters. So we need to convert it into standard units. So it's just times 10 to the power negative 2. So if you compute this, we're going to get that the potential from infinity to C is equal to 2.25 times 10 to the power 6 volts. So now if you move on to part 4. So if the voltmeter is connected between the points A and B, then the potential difference between C and A is equal to this. So the potential between C and A is equal to VA minus BC. So once again, all we need to do is substitute KQR, and we'll find out that since both these are equivalent in magnitudes, it'll equal 0. So now the voltmeter should read 0 at this point as well. So now if you move on to part B, the potential at any point due to the charged hollow sphere is once again equal to this. So we're just going over that once again. Then if it's at R, then the electric potential is constant. But however, if the point C is less than the radius of the sphere, then the electric potential is equal to this following expression that we've always been defining. So if the point A is at the center of the shell, B is at the inner surface, C is at the outer surface. So therefore, the electric potential at points A, B, C are the same, and all the points have the same potential. And that's the answer for part C. So they have the same potential. So this is regarding all the different points outside on the surface and on the inside of the sphere. They all have the same potential. So now as you move on to part C, if the charge changes the value of the potential from point C to infinity, is the only thing that changes. So the potential at infinity should be 0. So if the voltmeter is connected between C and the point of infinity, the potential difference between C and infinity can be represented by, once again, this same equation. So let me just go ahead and bring this down. That's not working, so let me just write it again. So the potential from infinity to C is equal to Vc minus V. And now, since we already did this in the previous equation, in the previous parts, we already know that the potential difference between C and infinity is equal to 2.25 10 to the power 6 volts. And that's it for this question. Thank you for listening.